So yeah, this talk is about gradient descent and how quantum algorithms can't improve upon it, at least in some context. And this is joint work with Ankit, Garg, Robin Kothari, and Praneeth Netrapalli when I was doing my internship at Microsoft Research. So to start with, I will recall what gradient descent is. It's a method used to minimize a function. It was introduced way back in 1847. It's a very straightforward method. So you have a function, you compute it at a point, and you find out its gradient. Now the gradient is the direction of steepest ascent. So you take a step in the opposite direction. And then you just repeat this process over and over. And the hope is that as you continue doing this, the function value is becoming smaller and smaller. And this simple algorithm is used a lot in practice. And because it's actually usable, because the gradient is actually cheap to compute according to the cheap gradient principle. It's just the same time as it takes to compute a function, you can also compute its gradient in linear in that same time. And it's also useful because there are many cases where you have lots of parameters, your input space is large, and you want to decrease some loss function and you need to find the correct parameters. This allows you to take like a 1D walk through this large space. And if you want to abstract out just this useful method, it's exactly what is there in the box above. All that you need are the function value oracle and the function gradient oracle. Now in this oracle model, you need the function gradient oracle. The cheap gradient principle above doesn't hold if you're computing using oracles. At least classically, if you have an n-dimensional function, you'll need n queries to find out the gradient from the function value. And the question we're dealing with is, what can we do with quantum algorithms? The first thing to note is that quantum algorithms can do really weird stuff. So for instance, with just one query to the function value oracle, you can actually find out the gradient. So one could hope that maybe with less than k queries, somebody can get the result of k gradient descent steps. And if this is possible, it would join many other useful subroutines that are used in quantum algorithms. Now, what if this is not possible? So people might be pessimistic about this hope, saying that gradient descent is a sequential algorithm, and how can a quantum algorithm speed up such a sequential process? And so if we want a negative result, we need to reformulate it a bit. We're also fine if you give me a quantum algorithm that doesn't go sequentially, that does some weird steps in the middle, as long as it finally outputs a point that is as useful as the point that gradient descent outputs. That would still be an improvement. So the question is, what is the use of gradient descent? Concretely, what can we say that gradient descent does? And for this, we use first order convex optimization as a proxy for gradient descent. So I'll now go into what first order convex optimization is, and we'll see how it relates to gradient descent. And then we'll see quantum algorithms, quantum Lower bounds against first order convex optimization. So the task of first order convex optimization is quite simple. You're given a convex region B, which we'll assume is just the unit ball for our talk. And you're given oracle access to a convex function f. So all you're given about the function f is the promise that it's convex. And you're given first order oracle access. That means that if you give the oracle an input x, the oracle returns to you the function value and the gradient value at f. Now, since you're just promised that the function is convex, the gradient might not exist, but we'll come to that soon. For now, let's assume that the gradient exists and see what this task looks like. So I haven't yet defined the tasks. What do we want to do given oracle access to this function? We want to find, ideally you'd want to find the x that minimizes the function inside this convex region. But this is too much to ask. So what you actually do ask for is an approximately optimal solution. It need not be the optimal solution, but the function value at your output point should be at most epsilon more than the optimal value. And here are some examples of this task in action. So here we have a convex function in which the red points at the bottom are epsilon optimal. On the right side, it's another convex function where the epsilon optimal points are to the side. And one would guess that the number of queries you need to make in order to find such a point would be a function of just n, the dimension, and epsilon, the accuracy. But it turns out that n and epsilon are not sufficient to, you can't bound the number of queries in terms of n and epsilon. And the culprit here is the slope. So if I take the same function, but give it a larger slope, then the number of epsilon optimal points naturally decreases. So if we want to actually bound the number of queries we need to look at n, epsilon, and the slope of our function. We're going to assume for our talk that the slope is always 1, at most 1. That means that the function is 1 Lipschitz. And this assumption is fine to make, because if you can characterize the complexity of this for 1 Lipschitz functions, then this also gives you a characterization for G-Lipschitz functions, where G is not equal to 1. So again, for the purposes of our talk, we're trying to optimize a function to accuracy epsilon, and we're promised that the function is convex and 1 Lipschitz. And now I have to tell you what happens if gradients don't exist. So a gradient is merely a point that passes, a plane, a hyperplane that passes through the point in question and stays completely below the curve. For convex functions, this is an equivalent definition as gradient. And if the function is non-smooth, for instance, this function, and you want to find out the gradient over here, there are multiple such hyperplanes you can use. For example, all these 3 hyperplanes are valid, and these are called subgradients. So the oracle axis that we have is going to give us the function value and the subgradient, any subgradient that the oracle wants, as long as it's a valid subgradient. And here's the formal definition of subgradient, which is equivalent to what I just said in words. So this defines the task completely for us. And what we'll see now is how gradient descent ties into this. So there are 2 famous algorithms for solving this task. One is the center of gravity method that does some kind of binary search, and it finds an epsilon optimal point in order n log 1 over epsilon steps. So it depends on the dimension here. If you have a really large dimension, the complexity of this is going to scale up. The other algorithm that we have is projected subgradient descent. This is it's the same as gradient descent, except that you're technically asking for subgradients. And anytime you go outside the convex region, you project back inside the convex region. So it's projected subgradient descent. Although it has such a long name, I'll just refer to it just as gradient descent. And the guarantee that you get with gradient descent is that you will reach an epsilon optimal point within 1 by epsilon square steps, regardless of the dimension. And this is why it's such a popular algorithm. So if we look at this a bit more pictorially, so we fix a value of epsilon, and we range our n from dimension 1 to larger and larger dimensions. What we've seen above is that in this first segment over here, center of gravity method has the better guarantees. And from this second segment onwards, it's gradient descent that has the better guarantees. But these are just upper bounds. How tight are these guarantees? Can we get better? This is what we'll discuss now. So we'll start with the classical deterministic case. We're looking only at algorithms that are deterministic. And it's been known, like a decade before I was born, that gradient descent is optimal, even if the dimension n is just 1 by epsilon square. So as soon as gradient descent becomes better than center of gravity method, it's already the optimal algorithm. So that's a very strong result in the deterministic case. In the randomized case, it wasn't that clear a picture. It was known from that same publication that it is optimal, but the dimension at which it starts becoming optimal was not yet known. It was initially a really large dimension. In recent years, it's been brought down. So implicitly in this publication, you can see that as soon as n is 1 by epsilon to the 4, gradient descent is already optimal. So the only question remaining after this publication is gradient descent optimal even in this region for randomized algorithms? It's worth noting here that although it wasn't known whether it was optimal up to constants, it was already known that it's optimal up to log factors. So it's already nearly optimal. So in our paper, one of our theorems is that in fact, it is optimal even in the second region over here, up to constants. So this is not that big a result because we're only removing a log factor, but the proof of this is quite simple, and that's something we like to share with everyone, a simple proof that gradient descent is optimal up to constant factors. So now let's go to the main thing that we're all here for, the quantum complexity of this. In the quantum case, this task has not been studied that well. Only in recent years it started being studied. And there was a recent paper by Chakrabarty, Childs, Lee, and Wu, and that showed that you need at least omega 1 by epsilon queries for a function with this dimension. So if anything, we're getting at most a quadratic speedup over gradient descent in general. But even after this paper, it wasn't clear whether you always can do quadratically better than gradient descent. And one of our theorems is, and our main theorem is that at least from this dimension onwards, 1 by epsilon to the 4, gradient descent is actually optimal even among quantum algorithms. So even after this work, it is currently an open question as to whether gradient descent is the optimal algorithm uh, before 1 by epsilon to the 4. Can quantum do better than that? So yeah, these are our two main theorems. Uh, if there are any questions, then I guess from now on, I'll be looking at the lower bounds. So if there are any high level questions about the area, I think I can take them now. All right. Yeah, so we can start with our lower bounds now. We'll start off with the randomized lower bound. In fact, both of the lower bounds follow a similar theme, so that's good for keeping in mind. What we're going to be looking for are functions that encode information in some sense. This is just a high-level overview, so if it's not rigorous enough, then just ignore it. And we want functions that encode information in the sense that if you're actually solving the task for this family of functions, then you have learned the encoded information. And every single query that you make to the function should access the information in a very controlled manner. So putting points 2 and 3 together, this kind of implies that if you're going to learn all of the encoded information, you need to make many queries. And hence, to solve the task, you need to make many queries. This is the high-level overview. Now let's instantiate for the randomized case. So we're going to start with a really simple function. It takes an n-dimensional input, and its output is just the coordinate that maximizes, so the maximum coordinate among x1, x2 till xn. This function is really simple to analyze. Its minimum is -1 by square root n within the unit ball, and it takes this value at this point here. Its subgradients are also easy to analyze. If xi is one of the maximums in this expression, then ei is a subgradient, because if I move along the direction of ei, I am moving with the slope of 1. And this function is convex because all the constituent functions in the maximum are convex. And we're going to use this base function, and we're going to encode some information into it. And what information we're encoding is this n-length string of +1s and -1s. And we encode it in the sense that the function depends on the string z, and it'll give you the maximum of z1x1, z2x2, and so on till zn xn. The minimum value this function takes, again, since it's so similar to the base function, is -1 by root n. And at this point, it takes that value. So what we want to also specify an epsilon that we want to optimize. And here we'll set it to be 0.9 by square root n. So an immediate observation is that if you find a point x that epsilon optimizes f, the function value at x should be negative, because it should be 0.9 by square root n close to -1 by square root n. So it is necessarily negative. So this is our function family. These are our parameters. Let's just observe a little bit about the behavior of the function, and that'll give us our lower bound. It's a fairly simple lower bound. So z is unknown to us as the queryers. What we're allowed to do is give an x. So here I'm taking this sample x. x1 is positive, x2 is slightly negative, x3 is heavily negative, and so on. And I'm going to query fz with this value of x. And the output value of fz can be seen as follows. You find the coordinate which has the largest absolute value. So that's, in this case, x3. x3 has the largest magnitude. And you look at the sign of z3. z3 is positive, so z3 x3 is negative. So we know that z3 x3 is not going to be the maximum in this expression because it's highly negative. The next largest magnitude belongs to x1. And we look at z1, that is also positive. So x1 z1 is positive. And in fact, x1 z1 will be the maximum value because nothing else has the same magnitude as x1. So just by looking at z3 and z1, we have figured out the value of fz. So the value of fz, at least on this input x, turned out to be dependent on z3, z1, and gave no information about the other values of zi. And if we take z to be uniformly at random, we'd expect maybe we can get lucky and find a few bits of z, but on expectation, we're only going to reveal around 2 bits of z before we get an index where zixi is positive. So we're revealing very little bit of z in each query. And when we actually do come across an epsilon optimal point, suppose this is it, then we know that z1 x1 has to be negative, z2 x2 has to be negative, so z2 has to be negative, z4 x4 is negative, so z4 is positive, and so on. So when you actually reach an epsilon optimal point, you can actually read out the value of z just from that point. So finding an epsilon optimal point means that you've actually learned z completely. And since every query is just giving you on expectation 2 values of z, this automatically gives us our lower bound. We need omega n queries in order to find an epsilon optimal point. And in our setting, omega n is omega 1 by epsilon square. So yeah, it was quite straightforward in the randomized case. And one could ask, what is the quantum complexity of epsilon optimizing this function family? Uh, turns out that quantum algorithms do get a quadratic speedup for this function family over here. You can do it in order square root n queries. And the reason for this is not Grover's, as it usually is for a quadratic speedup. So in this case, what happens is that for any subset S of 1 to n, you can perform an OR query over the Zi bits with a single query to some x. That is, for every S, you can find an input x, and then you query the function with x, and you'll get 1 if and only if this OR query is actually 1. So we basically get OR queries at a cost of 1 query. And we can use this along with Belovez's algorithm. And Belovez's algorithm uses such OR queries and learns a complete string within order square root n queries. So therefore, the complexity of this is order square root n. So since we're not getting a quantum speedup from this function family, we have to look to other function families. And the place where we look for our quantum lower bound is, okay, I'll come to where we look in a bit. First, let me just introduce the quantum query model. So the quantum query model is just a quantum algorithm that has access to this oracle OF. And it has access to this oracle. And so what does this oracle do in the quantum setting? That's what we have to specify. So the oracle acts on input registers and output registers. The input register is where we put our input query. So for each of our queries, we should have a separate basis state in our input register. So the way I've stated it here, this register is infinite dimensional. And all of the maths in our paper is finite dimensional. So this lower bound is actually going to work against any discretization of R to the n, any finite discretization of R to the n. It doesn't matter which discretization it is, you're going to get the same lower bound. But formally, the model is this, that the algorithm designer has to provide a discretization of R to the n. And then you will give them their oracle, which supports these values of x. And what the behavior of the oracle is as follows. It's as you expect it to be usually. For a basis state x and a basis state b in the output register, the oracle changes the output register to give you in a reversible way the values of f of x and a subgradient of f at x. Again, there's a discretization required over here in order for output register to be a finite dimensional register. But it turns out all these issues of discretization, they're not, I mean, we don't use any of them in our proof. They're only needed because our maths is finite dimensional. All that we actually require from our proof is the following statement, that if f and f prime are two different functions which have the same behavior at x, that means the function is the same and this function value is the same and the subgradient that the oracle would have output at f for f and f prime at x are the same, then your oracles should genuinely give the same output state if the input has the basis state x. And this is an extremely reasonable requirement, which I mean, it's hard to think of query models that don't allow this. They shouldn't. Yeah, it's very reasonable. And this is all that we're going to really need. So now let's come to the function family. We take motivation from this paper of Bubek, Zhang, Li, and Sitford, where they show lower bounds against highly parallel classical randomized algorithms. And they use a function that looks like this. So again, it takes an n-dimensional input. Again, it's a maximum over coordinates, but there's some kind of preference over here. X1 is preferred more than X2 and more than X3 and so on because of this slight gamma that's being subtracted from each of the subsequent terms. But gamma is really small, so it's not going to affect the global behaviors of this. So the minimum value is still going to be approximately -1 by square root k, and it'll take this value at this point. Right? So another thing to notice here is that there's a parameter k, and this maximum is only over k things. Even though the n is really large compared to k, we're only taking a maximum over k things, and our lower bound is going to be k itself. We're going to try for a lower bound of k with epsilon equal to omega 1 by square root k. So this might be a bit fast, but hopefully it'll make sense soon. The information we're trying to encode is a set of k orthonormal vectors. And how it's encoded is as follows. Instead of having x1 and x2 over here, we have v1 inner product x and v2 inner product x and so on. So basically what we've done is we've taken the previous function and just rotated it uniformly in this n-dimensional space. Again, it has the same kind of properties. And we set epsilon as before to 0.9 by square root k. And again, we're just going to look at the behavior of f and try to figure out how the lower bound goes. So let's take any unit norm vector x. Let v1 to vk be as above. We have this concentration of v1 inner product x and so on, which is basically that these values are going to be concentrated between 1 by square root n and -1 by square root n, or log n by square root n. So all these values are going to be really small. The gamma that we choose is actually going to be much larger than this interval. So what happens here is that these values are really small compared to gamma. And so our maximum, it practically looks like 0, minus gamma, -2 gamma, and so on. So the maximum is going to be at the first term, which is v1 inner product x. So with high probability, what you get from your first query is just v1. The function value will be v1 inner product x, and the subgradient will be v1. And v2 through vk are just going to be random from an n-1 dimensional space, because we know what v1 is. It'll be in the space orthogonal to that. I can't say it's uniformly at random, but it's nearly random. So this is what our first query does. For our second query, we already know the value of v1, so we can set it to be whatever it's needed for this epsilon optimal point. But since the other vectors are still random, they're still going to be concentrated in this small region. And since they're still concentrated over here, this is still going to look like minus gamma. This will still look just like -2 gamma and so on. And so except for the first term, v2 inner product x minus gamma is going to be the maximum of the other terms with high probability. So in the second query, we are with high probability only going to get v2. And in our third query, we can set the values of v1 and v2 inner product x, and the other ones are still uniformly at random and so are very small. And so we can do this for k-1 queries. After k-1 queries, vk is still nearly at random. So if you're going to output your answer without making the kth query, vk inner product x is going to be really small, and our function is going to take a large value, and it's not going to be epsilon optimal. And this is the rough idea behind the lower bound. It's forcing the algorithm to go sequentially. So even though there's nothing, it's not gradient descent, the function that we've embedded over here in this optimization task is forcing your algorithm to move in a sequential way. And that's what ensures that quantum cannot get a speed up here. Quantum must also move sequentially. To formalize the statement that quantum must move sequentially, we use the hybrid argument. How much time do I have left?
Actually, we are now entering the Q&A time frame already, so maybe if you speed up a little bit, just
All right. Sure. So the way it works in the hybrid argument is you can create your first query, which might cover many points, and you pass it through the oracle and you get your answer. So what you do over here is you replace this oracle with a limited information oracle. So this oracle only has access to the point v1. And we've already argued that v1 inner product x is most likely the optimal, is most likely the value of f itself. So for most of your input points, the answer doesn't change by the fact that you've changed this oracle. There might be a few points where your answer changes, but that's going to be a very small mass of your superposition. So after having changed this oracle, the output states of the oracle are almost the same. So it doesn't matter that you change the oracle is the idea over here. And when you go to the second query, if you've changed the oracle, then this query point only depends on v1 because the first oracle only depended on v1. So we can make the same argument again and say that we can actually change the second oracle and choose this function instead for the second oracle. And again, our output state is going to change only a little bit. So I'm not being formal here. I don't have the time for it. But you can continue this for k-1 steps. And you'll say that even though I've changed all of your oracles, your algorithm's behavior didn't really change. It only changed a little bit. And the k-1 times corrupted algorithm has a state that's independent of vk. It didn't have any oracle that had access to vk. So with the k-1 corrupted oracle calls, you won't be able to output a state, output a point that is epsilon optimal. And therefore your original algorithm would also have failed. So that's a very quick run through of the hybrid argument. There are some small notes to make here that we actually modify the function a bit to account for queries that have norm larger than 1. And we note that this above argument gives n as small as 1 by epsilon to the 6. But with more modifications taken from the same paper, we can bring it down to 1 by epsilon to the 4. And that was the theorem that I had stated early on. There is another result that we have that if you have a promise that your function is smooth, then the algorithm that we want to look at is accelerated gradient descent. And we show even there that quantum cannot do better with a nearly identical proof, except that the function requires smoothing. The open problems are primarily what happens if n is smaller than 1 by epsilon to the 4. Do you actually get a speed up over gradient descent? What other classes of optimization problems get quantum speedups? We noticed that one of them had a quadratic speedup. Are there natural classes that get speedups? And in particular, this function here, where you've rotated the basis so you have v1, v2 till vk, but you don't have the gamma terms. So we have a lower bound of order square root n, square root k in this case, and an upper bound of order k, but we don't know where the quantum complexity of this function actually lies. Thank you. That concludes my talk.
All right. Yeah, many thanks for this interesting talk. And yeah, I just, in the interest of time, I would just refer yeah, to the Slack channel and the roundtable at 12:30 to discuss more detailed questions, right? I just want to mention one question by Jan Lucas Bosse. We always assume that we have some quantum oracle for the gradient, right? So right. I guess this refers to whether if you can like directly have access to the gradient or the function, I guess.
So in this case, we do have the oracle does give us direct access to the gradient.
Okay, yeah, okay. And I just want to mention there's already a quite long thread of replies to this question in the Slack channel. So yeah, please just head there and also, as I mentioned, to the roundtable at 12:30. Okay, with that, thanks for your presentation, and then maybe see you at a roundtable.